The seminar is going to be recorded, and the plan will be that we will invite our speaker to give us presentation, and during that time we will not accept questions, but you may put your questions in chat, and then at the end of the talk we'll open the mic for questions, and also address any questions that have been dropped into the chat itself. For those of you who are joining for the first time, the talks on the series, just to make you aware that the talks are being hosted by the Automatic Control Engineering Network, which is an EPCC funded network in the UK promoting the area of control. And if you are interested in finding more out about that network, I'll refer you to the ukcontrol.org website, or indeed if you follow the links in the various emails that you would have exchanged signing up to this event. Okay, it's my great pleasure to introduce our speaker today, Professor Raphael Jungers from UC Leuven in Belgium. His research interests lie in the field of computer science, graph theory, optimization, and control. He has a PhD in mathematical engineering from UC Leuven, an MSc in applied mathematics from both the École Centrale de Paris and from UC Leuven. Over his career, he's held various positions from the University de Bruxelles, at the Laboratory for Information and Decision Systems at MIT, at the University of La Quella, at the University of California, Los Angeles, and most recently on a sabbatical at Oxford University. He has an FNRS, a BAF, and a Fulbright Fellow, and he's held various editorial responsibilities, including associate editor roles at IEEE CSS, conference editorial board positions at the various journals, and I guess currently he's a senior editor for the Non-Aeronautics Hybrid Systems Journal. He was the recipient of the IBM Belgium 2009 award and finalist of the Ersum Caribbean Award in 2011. I guess some of his more recent accolades is he's been a recipient of the European Research Council Award in 2019. And most recently, he's been elevated to IEEE Fellow status. So today he's going to give us a talk on the area of, I guess, his own research in recent times has been around data-driven methods, and he has his talk. I will let him introduce himself. So I hand you the floor to Raphael to give your presentation.
Thank you very much, Sean, for this nice introduction. Thanks a lot for the invitation. I'm honored, very glad to be here. Yes, today I'm going to talk about data-driven methods in controls. This is joint work with several people from my team and from outside my team, but mainly it's collaborations with my senior postdoc, Guillaume Berger. Guillaume is now in the job market, so if you like anything in the talk, bear in mind that it's most probably due to Guillaume. Okay, so is this slide okay? Moving. So a bit of actually I'll make a long introduction, and then I have several topics. It's more potpourri of research topics on data-driven techniques. I might skip one to stay in time. I'll make a very long introduction to share global ideas, and we can discuss it together afterwards, and make sure I keep time for remarks and discussion. So yeah, as in many fields of engineering, data are becoming a new paradigm in control due to several facts, I think. First, the surge of many mechanical, can you see me? I'm not sure you can see me anymore, but maybe, yeah? Or yeah, maybe it's not a big deal, you see my slides, right? So anyway, you can see my slides. So due to the apparition of many sensors in our engineered devices, with a lot of coming data, but it's also due to upcoming challenges in engineering, where models are becoming increasingly complicated, and and sometimes it's hard to control a system based on a model, and due to that, people are shifting to a data-driven paradigm to control systems. And examples here are an artificial pancreas controlled through data that are harvested through sensors. Here, smart cities and smart grid applications. I think the recent events in Spain convince us that indeed the systems are becoming increasingly complex. And sometimes we better stick to data rather than to a complex model to understand them. So yeah, summarizing, in some situations, of course, a data-driven approach can be more flexible, more accurate, or even more efficient. And that's what we're going to see today. So I'll insist on two important challenges in data-driven control. First, data collection. Of course, there are many data pouring from these sensors, right, as we said, but still, it's often a goal to minimize the number of data harvested, if only because it's a lot of trouble to process them. So we'll try to design algorithms that need as few data as possible. And the second problem is data exploitation. What can you say with all these data? Of course, you can have a hint, right? When you observe a system, you can think, oh, it's stable, unstable, or whatever. But what can you really prove? How can you derive firm guarantees, theoretical results, quantitative proofs from the mere observation of data? And we'll see a bit about that today too. So let's see a few examples of data-driven control problems. And by data-driven, I mean we do not use a model, but we rely on our analysis just on the observation of data. So a first family of interesting problems, I think, is identification of cyber-physical system. Here we have a hybrid automaton. It's a famous model for complex systems. A hybrid automaton is made of actually several systems, which we call mode, and the system can behave in one way according to one mode or another, depending on time or on where it is in the state space. And so it can jump from one mode to another if some condition, which can be an algebraic inequality, for instance, if some condition is satisfied. And so the system has actually several behaviors. So when you observe the behavior of a system, you would observe something like this, right? Something which looks normal, and then suddenly the system changes of behavior and changes again, etc. So how can you build, if you just observe this kind of traces, how can you build a model which accurately represents the behavior of the system? So it's the topic of a vibrant field for the moment, and in recent years it has become clear that this is a very hard problem. So typically we have many negative computability results about hybrid systems or cyber physical systems identifications, but still people are working hard, and some techniques work well in practice to connect observed data with and to reconstruct a model from them. Another popular problem nowadays is data-driven safety analysis. So you just observe data. Here data are traces of the system, as they say in computer science, or trajectories, as we say in control. And you want to make sure that these trajectories do not and will never reach an unsafe set, which corresponds to a state of the system in which you don't want your system to be. So of course you observe, if you observe that the trajectory goes there, you know it's unsafe, but what can you say if you just observe that it stays in this green part? Well, something you might want to do is to build a so-called barrier function that would be a barrier between all the states which your system can visit and the states where your system cannot be. Yeah, and nowadays a popular set of techniques to do that are so-called data-driven symbolic control approaches. In symbolic control, people try to discretize the state space and then to formally prove local behavior of the system. So prove that if the system state is close to that state, then we can guarantee that the system will be at the next step in this set of states. And the idea is that if locally you can prove formally that your system behaves in some way, well then, since you have discretized, you can represent the overall global system now with a finite number of states and use tools from graph theory or from machine learning to analyze formally this system and provide formal guarantees. So this is a little advertising for a tool we are developing in my team, Dionysus. It's a software platform coded in Julia where we are trying to develop and implement data-driven formal analysis tools. So a typical question here is, how many data should I sample in order to have a formal guarantee, right? If I want to formally guarantee that when I'm in this discretization of the state, at the next step, I will arrive somewhere in this weird shape, how many data should I sample in this little square to make sure that my statement is correct, right? So this is typically a type of question that we are wondering. Another family of problems are change constraint problems. So here we have a control problem with a constraint, but a probabilistic constraint. For instance, I want my robotic arm here to avoid a box, but I'm not sure exactly where the box here is. I have a probability distribution describing the position of my box. And I want to make sure that the trajectory, except if I'm very unlucky, that the trajectory will not hit the box. Okay, so change constraint problems are problems with probability distribution and constraints, and a given epsilon, which is a bound on the probability that the constraints will be violated, right? So I want to optimize some criterion under the constraints that my solution will not violate the constraint, except maybe a small portion of the support of this probability distribution. Okay, so many of the problems I presented before, and many problems in controls, can often be formulated as optimization or feasibility problems, right? We all know that. For instance, the computation of a Lyapunov function, right? It's an equation here which can be represented often as a semi-definite programming, for instance, right? I'm asking to find a function v such that for every x in my state space, the value of the function at the next step, f of x, is smaller. Oh, there's a v missing here. Sorry, is smaller than v of x, the value of the function here. Sorry about that. My change constraint problems, which are presented before, amount to optimize some criterion here, finding a shortest path in the state space, such that the probability to avoid obstacles is larger than 1 minus epsilon. This is the constraint. So that's well known, but there are two classical problems in this setting. First, often these problems may not be tractable, right? To optimize, to find a function v and to represent a function with a computer, to find this function with an optimization program, or to solve a change constraint problem, are notoriously complicated problems. Even more, sometimes the problem is actually not completely known, right? Sometimes I do not know my dynamics f, or I do not know the measure, the underlying measure of my constraints, right? And we'll see examples later. So for these two reasons, people are moving now to a data-driven approach for these problems. And the idea is very simple. It's what we'll call the scenario approach. And it's a very simple idea. It's rather than solving the actual problem, the complete problem, well, let's just sample constraints or sample points and solve the problem on a finite number of samples with classical tools, right? So here, for instance, for the change constraint problem, I have a distribution of constraints. I would like to optimize such that the probability of avoidance is smaller than epsilon. Well, something I could do is to sample many constraints and then just ask that my trajectory satisfies at least the constraints I've sampled. And probably if I sample many constraints, then most of the constraints are satisfied in this distribution. That's the idea, right? Okay, and so that's what we will do today, but we'll do that in the framework of scenario of decision making rather than in optimization. Many problems in control are decision-making problems, and they feel a bit like the problem I described before, but are a bit different. So what is a risk-aware decision-making problem? It consists in, it aims at finding a solution X, a decision X, among a decision space. For instance, X, capital X would be the set of possible path for my car, and I want to decide of one particular path, right? For a data-driven autonomous car, for an autonomous car trajectory planning, my set of decisions would be the set of possible path, and I need to choose one. And how do I do that? I have a set of constraints on the trajectory, and typically these constraints are probabilistic because I don't know exactly what will happen in the future, right? So for instance, there can be pedestrians all over the place, and for each position, there's a probability that a pedestrian shows up there, right? There can be other cars, and there can be stupidly small probabilities for some other trajectories, right? So, and now, given these probability distributions, probably I will neglect that one, right? Because the probability is silly. But given, if I knew all these probability distributions and I knew all the possible decisions I could take, the goal of a risk-aware decision algorithm is to output one decision, X star, okay? Such that almost all the constraints are satisfied. So the measure of the violating constraints is smaller than epsilon, okay? Sean said, we leave the questions for the end, so I hope I'm clear, but if I'm really not clear, please don't hesitate to interrupt me. Okay, so that's a risk-aware decision-making problem, and the goal is to find a decision X star given a set of probabilistic constraints. Now we can apply the same philosophy of scenario approach, which is, suppose I don't know really the probability distributions, right? If I'm planning the trajectory of a car, of course I do not know the probability distribution of presence of pedestrians and of cars everywhere. But something I can very easily do is to sample constraints. I can observe the city for some times and sample the constraints, and then choose for one trajectory depending on the samples I observed, right? Makes a lot of sense. I think that's what we would do in practice, and it's very natural. Now the question, which is much more tricky, I think, is what can we say about the initial problem, about the probability P that all my constraints are satisfied with X star, knowing that I've only sampled the finite number of constraints. Okay, I have very few technical slides, but here is one, because I want to make sure we agree on this concept of scenario decision making. So again, we have a set of decisions, X, capital X, and then there are constraints, right? Just like in optimization, a constraint is actually a subset of all the decisions I could make, right? I can have several constraints, several Z in capital Z, okay? And I say that X satisfies Z just if X belongs to that set, okay? So a constraint is actually just a subset, right? And then I have a probability measure. Crucially, I have a probability measure P on this set of constraints, okay? So that's part of the given, or at least we assume it exists. Sometimes I will not know it, but we always assume there's a probability measure on the constraints. And now what I will do in the scenario decision-making approach is to sample a few constraints, capital N of them, okay? And then I will feed them in an algorithm, okay? And given the observed constraints, my algorithm spits out an X, a decision X, okay? And once I have a decision X, I can define the probability of violation of this decision, which is simply the probability that if I sample now a new constraint Z, not one that I already solved, that I already observed and used in my algorithm, but if I sample another one, what is the probability that X will violate it, right? So we call that the violation probability, or also the risk of the solution X, right? People in machine learning, among others, call it, or in economics, call it the risk, right? The risk of my decision X. And observe that this violation probability is a random variable because it depends on the output of my algorithm. And in my algorithm, I fed a random variable, right? So clearly, the violation probability of the solution I will retain is itself a random variable. Now, we aim at a PAC learning framework, at PAC learning results. What do I mean by that? I mean that given some algorithm ALG, I want to understand what is this risk. But since it's a random variable, I will only be able to probabilistically characterize this risk. And so typically a PAC bound for a scenario decision algorithm would be a bound, a lower bound on the probability that the risk is small. Okay, so given a target risk epsilon, I will have a well-defined probability that my risk will be lower than epsilon. And I want to provide a lower bound on that probability. Okay. And so here in this work, we want to characterize learnable problems, which is problems for which we can actually provide a lower bound on the fact that the risk is smaller than epsilon. Okay. So this sounds very much like techniques they've studied in machine learning. So let me do a little detour on. I will do a little detour on PAC learning in classification. And typically in classification, they have two families of bounds in order to bound the risk being smaller than epsilon. First, complexity bounds. You've probably heard already about VC dimension or Rademacher complexity. And basically, these bounds rely on the question, how complex is the decision space X? Okay? If the decisions I can make are very simple, like yes or no, maybe, then probably I don't need too much data to find the right answer with high probability. But if I can take many different decisions, if the set of decisions is very complex, then I would need a lot of data to make an informed decision, or maybe it's even impossible to make an informed decision, and then we would have a problem which is not PAC learnable. And the second family of bounds are so-called compression bounds, and the idea here is to study the question, how many constraints do I need to make a decision? We'll come back to it more precisely later. So now here is the plan of my talk. After this long introduction, I want to survey a few results that we have provided, and at first I want to talk to revisit these conditions for PAC learning from machine learning. I will reintroduce them more in details, and then we will reuse them for scenario decision-making problem. So you probably know about this, right? If not, I'll quickly survey it. So this PAC learning bound have been developed in the framework of classification. So what is classification? I receive pictures as a computer. A computer receives pictures of cats and dogs, and he wants to understand whether this is a cat or this is a dog. So we need to classify these pictures, and these pictures are represented in a feature space, usually a Euclidean space. So here I summarize my pictures in 2D. Of course, in general, the state space would be much larger, but still it's a Euclidean space. And so I want to understand the region in this Euclidean space, which corresponds to pictures of dogs, and the rest would be classified as pictures of cats. Okay, and I have a set of possible classes which are predefined a priori, and here I use squares. You could have all sorts of predefined classes. Here I will use squares to single out the dogs with respect to the cats. Okay, this is the family H, and in my case, this is the set of rectangles. Okay, and it turns out that the difficulty of the task is only related with this family of classes, And how is it related? Well, via the VC dimension. What is the VC dimension of a family H? It's actually the largest number of points that can be completely shattered by my family H. And by shattered, I mean that I can provide any arbitrary coloring thanks to one particular classification in my family. So as you can see here, I can shatter this set of 4 points. I can shatter it, meaning I can color it however I want. If I want to color these 2 points in red, I can, for instance, take this class. If I want to color these 2 points, I can take this class, etc., etc. Okay, and actually it turns out it's the maximal number of points that can be shattered. If you take 5 points in the plane, you'll never be able to shatter, to color, to make an arbitrary coloring of them with rectangles. And so the VC dimension of rectangles is 4. And we have this famous theorem, which says that if the VC dimension of my class is finite, then it is PAC-learnable, meaning with a finite number of data, I will be able to give a lower bound that the risk is smaller than epsilon. For any given epsilon, right, there exists a number of samples which is sufficient to bound the probability that the risk is smaller than epsilon, because the VC dimension is finite. Even more, this theorem is true for any underlying measure. So whatever, because in practice you do not know the measure, right? We already commented on that. And whatever the measure is, provided that the VC dimension of my class is finite, then you only need a finite number of points to provide a lower bound on this risk being small. There's actually another similar result in the machine learning literature, which is the compression theorem. So we say that an algorithm has a finite compression size d if the following happens. So this is my data, right? And as you know, in classification from data, you will output one particular class in my family. So one particular classification, one rectangle, which comes from the points you've sampled. And we'll say that this algorithm has finite compression if there is a number d, here d is equal to 5, such that from all the observed data, you can always compress it to a critical set of observations, such that from this finite small number of observations, you can reconstruct the same solution. Just a little break. Can you still hear me? I want to make sure that I'm still well connected. Can someone?
Yes, we can hear you.
Okay, yes. Thank you, Kate. I appreciate it. Prefer to make sure. It already happened to me. I won't tell you the story. Yes, so if the algorithm is compressible in that way, right, we only need a small number of data. We don't need all these data, actually. We have a map that extracts the critical point, and with this bounded number, bounded by d, of observations, still we can recover the very output of the algorithm. If we have this fact, then again, it turns out that my class is PAC-learnable. I only need for any epsilon, I only need a finite number of data such that I will be able to bound the probability that the risk is smaller than epsilon. Okay, it turns out even more, and I think this is a deep and beautiful result, that these two sufficient conditions are actually also necessary. So it turns out that the only PAC-learnable classifications are with classes of finite VC dimension. Okay, so we have a characterization of something very, very quite deep, right? When can you generalize from a finite number of observation? Can you generalize your classification to the whole set for any underlying probability, and make sure that you have a bound on the risk? These two conditions are actually equivalent: finite VC dimension of finite compression size. And I think this is quite a deep result. But our problem is different, right? Remember, our problem, it's a scenario decision-making problem where we have a probability distribution on the constraints, and we want to select one decision X. However, it sounds a bit similar to the classification problem. We do not want to classify, we want to select, but aren't these two problems equivalent? Actually, in some sense, the decision-making problem is a particular case of the classification problem, what we call the monochromatic classification problem. Why? Well, because I can see my decision X star as a classification of my constraints, right? Here I sample constraints, and then I output one X star, which probably satisfies all the constraints I've sampled, right? It would be stupid to violate them. It will satisfy other constraints. And of course, in the world of all the constraints, some will be violated by this, right? So somehow, implicitly, my decision X star is a classifier among all the possible constraints. It will define the set of constraints that are violated and the set of constraints that are satisfied. And so we show it rigorously in our work, of course. Our scenario decision-making problem is actually a particular case of a classification problem with the very particular property that we only sample positive constraints. That's why we call it the monochromatic classification, because here we only sample constraints that must be satisfied, right? In all the applications I've mentioned, I never sample constraints that can be violated, right? I only sample constraints that must be satisfied. So we are in a particular case, and this implies that the PAC learning conditions that I've introduced before are sufficient conditions for learnability in our scenario decision-making cases. And we were very much interested in characterizing these scenario decision problems that are actually learnable, because it reminds us of the classification problem, where we have a clear characterization of the PAC-learnable problems, while here, as I've said, and of course all this is made formal in the works, the two sufficient condition are only sufficient condition because we are in a particular case where of monochromatic sampling, as I called it. So we have from the literature these two sufficient conditions for a scenario decision making to be PAC learnable, and in fact they are in this particular case of monochromatic sampling, they might even not be equivalent. So that was the state of the art when we started our work. And actually, we showed that, strangely enough, in this particular case, these conditions are not equivalent anymore. And we provide an example of a problem which is compressible with a finite compression D, and so it is PAC learnable. But we show that it has an infinite VC dimension. And on the contrary, we show a problem which has finite VC dimension, and hence it is PAC learnable, but it is not compressible. It does not have a finite compression scheme. Okay, so this shows that these conditions are sufficient but not necessary. But really, we wanted to find a necessary and sufficient condition, just like in the classification problem. And so we proposed a necessary condition now, which we called having finite DVC dimension for decision VC dimension. We had conjectured that it was a characterization of an algorithm, a scenario decision algorithm being PAC, but we found a counterexample. So right now we do not have a nice, clean characterization of PAC learnable decision problem, just like we have in classification. We made another conjecture, but it's still open for the moment, so I have no idea whether it's correct. But I think it's a nice problem to really understand what makes a problem PAC learnable, just like this beautiful result they have in machine learning for classification. Okay, so we have applied these change constraint results to the stability of hybrid systems. I think in the interest of time, I will skip this part because it's slightly independent. And I want to talk more about change constraint motion planning, because it's a collaboration with British researchers, very exciting collaboration to me. So let me tell you a few words about this. This is a collaboration with Nick Hall's team from Oxford. They were kind enough to expose me their problems when I was there on sabbatical. I spent a wonderful year in the UK, by the way. I really loved it. So what is their problem? They want to steer a robot between obstacles. And the way they do that is to parameterize a trajectory with waypoints. And as you can see, they optimize the position of their waypoints with stochastic optimization. That's why their toolbox is called VP store. But the obstacles are static, okay? And they solve an optimization problem with stochastic heuristics to find the best trajectory for the robot. Now they want to move to chance constraint VP store, so a chance constraint optimization for the trajectory of this robot, because the obstacle move or they can be in random places, and so they want to find smart trajectories, knowing that there is an underlying distribution for the position of these obstacles, and they can be complicated. Okay, so this is exactly what I presented before. And the way we propose to solve it is with a scenario approach, meaning that the distribution here can be very complicated. And we know that finding the shortest trajectory such that the probability of collision is smaller than epsilon is actually very complicated. It's NP hard, etc., to solve it exactly. But so what can we say from data-driven scenario approach, where we just sample positions for the obstacles, right, with our probability distribution, and then we don't have probability distribution anymore. We just have a set of here 5 constraints, and we find the shortest path that avoids these five constraints. Well, this is a very complicated non-convex optimization problem, so it's hard to find PAC bounds, but Guillaume was clever enough to provide a complexity bound on this for this situation where the obstacles are ball-shaped. So in this case, even though the problem is non-convex, Guillaume was able to provide a PAC learning bound, meaning, so let me give you the theorem, and here you have an animation where the robot moves, so it has a stochastic position and the robotic arm avoids it. So that is the theorem, meaning if the obstacles are balls and you're given the probability distribution on the positions of these balls, well, one can compute a number n such that you sample n positions for these balls, you find the shortest path avoiding these m balls, and finally you can compute an upper bound on the probability of collision, except if you were unlucky, right? Remember, there's always this risk is a probabilistic, it's a random variable, as we said, but we can bound the probability that the risk is small. Okay, so it's really a PAC bound, as I've described before. This is nice, I think, a beautiful case of a non-convex problem where still one can provide a PAC bound. However, the number is still very large. I must say, all these PAC bounds have a very large, necessitate a very large number of samples. And that's what motivated the last research topic I want to tell you about today, where we try to be more reasonable in the number of points we sample, okay? So how do we do that? We do that online via a refined iterative approach. And this is inspired from stochastic MPC, where you actually iteratively solve your problem, right? By using what you know at some point, and then you solve your problem, and then you refreeze and you observe and you re-optimize your problem, your solution. There's a tension here, right? Because so in a stochastic optimization problem, so what you see here are the obstacles. Each point of color is an obstacle, and the traces that you see there are the projected trajectories, which are probabilistic trajectories for the obstacles, right? And so why are there all these traces? Because at every fixed time, when you see the robot freezing, just very fast, when you see it freezing, it simulates trajectories for all these 5 obstacles, And then it solves the optimal control problem given these trajectories. And it does that many times, right? As soon as it iterated of one step, it reobserves the new position of the robot. It simulates all these traces, and then it finds a new trajectory to go, right? It works pretty well. It avoids actually all the obstacles by doing so, by re-estimating the optimal strategy at every step. But there's a tension, which is if you sample a lot of trajectories for these obstacles, then it's going to take you a lot of time to compute the optimal control for the next step. And then you will have a lot of delay between the moment you freeze and the moment you implement your new optimal strategy. And so our idea was to use these results from scenario decision making to find the right trade-off, to sample not too many trajectories, but just the right amount needed so that you would find a meaningful control action for the next step. And you don't want to sample too many, because if you do that, you will lose time, computational time, and so you will only be able to implement your new control action too late in the future. Okay. So that's a new approach to stochastic MPC that we propose. And the goal, again, is to maximize the update rate, to be able to update the MPC controller very fast. And we do that by minimizing the number of samples. But we use the scenario approach to smartly select the number of samples we need and to have a guarantee that we have still enough samples so that our control action is safe. So we have a theoretical work on that. We provide an analysis of an idealized situation where we assume that there's a fixed optimization problem, and we'll relax that later. And we solve it many times, every time for a number of samples that we choose. And then when we solve it, we have a kind of oracle that gives us the risk associated with this solution, the probability of violation associated with this solution. And this oracle, of course, what can it be? Well, in practice, a posteriori, once you have computed your solution, you can often estimate the risk very rapidly, efficiently, and precisely, just by resampling new constraints, right? And then you have a kind of Bernoulli test, a very elementary test from statistics. You can estimate the probability, the proportion of constraints that are violated, or the probability for a constraint to be violated, just by sampling a set of constraints and then observing whether the solution you have violates them or not. So in practice, one can have fairly good implementations for these oracles. And so how the algorithm works, what is the problem setting? You fix a number N1 of samples, you observe a risk V1 associated to the solution you have, and then you pick a new N2 number of samples, you sample these constraints, you obtain a solution, and the oracle gives you the risk associated, and you iterate by doing so. And so, in fact, you have a bunch of observations here, which is for N1 observation, for N1 samples, you have the risk V1, for NK samples, you have the risk VK, etc. And the goal is to, now given this, this data, to estimate the true relation between the number of samples and the risk that you obtain. Okay, so we have a technical assumption. I don't want to spend too much time on it, but it's an assumption which is, for instance, verified for convex problems and many more problems. And we apply a standard, actually, maximum likelihood estimate, given this assumption, in order to refine our estimate on D, which is the parameter that describes the relation between the number of samples that we make and the risk epsilon that we have. Okay, and so by doing that iteratively, we can converge to the exact number N of samples that we need if we want to ensure a certain risk epsilon. Okay, so for instance, we have this optimization problem, and the constraints are infinite here, and with this distribution. And what we can do is to sample N constraint and then observe the risk, and then in view of the risk that we have observed, reiterate, right? And here, as you can see, that's what we do. I'd rather use the next figure, it's nicer. So here is a description of our experiment. First, for a fixed distribution. As you can see, we start with 50 samples. We think we need a lot of them, but we realize that the risk is actually very small. And so we say, okay, we can actually sample much less points. And here we see that the risk is a bit too high, etc. And then by doing this, we converge to a number of samples, n, which is roughly 20, right? And we observe that the risk is exactly the one we needed. Okay, so we do that in an iterative way, in a learning fashion. And here is the parameter that summarizes this relation between n and the risk, which we learn, right? And we learn a parameter, and at the end, we converge to what we think is the true parameter. And indeed, we verified the solutions we have, and we see that most of the time, the risk is smaller than 0.10. So here the goal was to have a risk smaller than 0.10 with a confidence of 95%. And that's actually what we achieve. We achieve even a little bit better, right? Sometimes the risk is larger than 0.10, but this happens only 5% of the time. And again, we are in a PAC learning framework, so that's what we are aiming at, right? We will do mistakes from time to time. It's a statistical result, but we can bound the probability that we make mistakes, which is 5%. Okay, I want to remain on time, so we applied it even to systems which do not satisfy our assumptions, and it works pretty well in obstacle avoidance for smart robots, for instance, etc. But again, I want to remain in time, so let me jump to the conclusion. So I think that data-driven methods are very promising in control for black box control, especially in stochastic environments. There are huge challenges, especially theoretical challenges. I think all this is quite complicated, in particular because machine learning gives us probably approximately correct results, but we often need more in control. And I skipped that part, but that was an example where we need probably correct, but not probably approximately correct result. And so by using the specificities of the system, sometimes we can leverage these results from machine learning, but go beyond them, thanks to the specificities of the control system we are studying, to provide firm guarantees on the system. So PAC bound can be conservative, as I've said, right? Sometimes the bounds on the number of samples needed are huge, but there are other approaches or refinement of these approaches. And what we propose here is an online estimation of the actual optimal number of sampling that we need, which often is much smaller than what the theoretical bounds give you in a machine learning setting, right? By learning, we optimize, we refine our estimate of the number of data points we need. And finally, we have an open question, right? Is there a necessary and sufficient condition for PAC decision algorithm, just like there is for classification? We provided partial answers, and I think it's a nice, interesting theoretical open question. And with that, I'll conclude. Again, thank you very much for your attention. I hope I left time for a few questions at least.
Thank you, Raphael. Yes, we have, you're spot on time. Thank you. So yeah, we have time for questions. So I think, let me see, one question in the chat, or one or two questions. So let me see the first one. So this is from Venkurtaman. How do you sample your constraints from its distribution? Should you do bias sampling by sampling more from around the mean of the distribution or more towards the tails to get more informed worst case decision making?
Okay, thanks for that. Well, I think it depends on the setting, right? In some situations, you do have a probability distribution. It's the classical so-called chance constraint optimization problem, which they studied starting in the 2000s, I think, in the operations research community. And there they know the probability distribution, and indeed there you can fiddle with it and apply tricks to refine your analysis, depending on situations. In controls, in most of the applications I see, we actually do not know the probability distribution. And by sampling, I just mean observing out there, right, and looking at situations. And so there, I do not think you can fiddle with the probability distribution because it's underlying. But the beauty of these PAC learning results is that you do not need to know it, and the results are true, whatever is the underlying. So that's what we call distribution-free results. But indeed, in the setting where you know it, I think you can improve your analysis by fiddling with the distribution. And I'm not very familiar of this, but it would certainly make sense, I think. Now there's a second question.
Yes, there's a second question. Perhaps you might read out your own question rather than me reading it out for you.
Yeah, I can read. Am I audible?
Yes, you are.
Yes.
Indeed.
Yeah. So thank you so much, Raphael, for a fantastic talk, first of all. So my other question was like, on the risk-aware planning task that you actually gave, because I do some research on risk allocation, and I was just wondering, how would you do a risk allocation for multiple obstacles here? Because, what you said is like you sample for each obstacles, and I'm just curious, like, how would you do a risk allocation based on multiple obstacles? Because one obstacle might need more samples than the other one at a particular time in the space to actually satisfy a risk. So I think that's I would like to hear your opinion on that.
Okay, so that's a very interesting question, I think. So that would be, so we assume that we have one measure of constraints, right? And so
risk budget, which we have to allocate. Yeah.
Yes. We haven't thought of that. So I guess it connects maybe with multi-armed bandit problems, or where you need to choose what you sample, or definitely it must connect with classical problems in statistics. So I think it's a beautiful opportunity of generalizing our results. We haven't walked in that direction, but indeed you're right. It will make a lot of sense. We can talk about that and write another paper together.
Sure. Definitely. Thank you so much, Raphael.
Thank you. I appreciate.
Yeah.
And anybody else? I don't think there's any other questions in the chat, so I can open the mics now for verbal questions. If anybody has any verbal questions.
Hi, can you hear me?
Yes,
Nikos, yes.
Yeah. Hi, Raphael. Thanks very much for your talk. That was really inspiring. Thanks a lot. I just have a short question. What's your opinion about applying this framework to identification or to estimation, and specifically into model updating or into when detecting changes in let's say in the time-varying models?
Yeah, I guess it's possible, right? You only need to represent your problem as an optimization problem, and then all the results can be mechanically applied. So I think it's interesting indeed. We haven't thought in that way. However, I remember discussing with my researchers about, because there was so much work, right, in identification, in control. And strangely enough, before people like Campi and Galati and Calafiore in 2008, for reasons I do not understand, or I don't know such results for identification. So I think maybe I'm missing some parts of the literature, but I remember asking around mechanically applying these results to the optimization problem that you get in SysID might lead to interesting results, I think.
Thanks. Thank you.
Very good. One last opportunity for questions. If there's anybody, any other questions? Okay, I just have one question. Just Raphael, I think it was the previous to last slide. You were showing the results for convergence to the optimal sampling size. So there's a single optimum value, or would that change over time? Will these methods still apply in a time variant scenario where maybe as things change that the optimum number of samples would change, or is this a universal result?
Yeah, thanks. So our theorem works with fixed distribution and with an additional assumption, which is a classical assumption, because basically we assume that the risks follow this probability distribution, which holds only in some situation. But in fact, in practice, it works. And the reason is that intuitively, locally, an optimization problem behaves like a convex optimization problem. And even, so that's when the assumption is violated. And here, even the complexity varies. So the number that you need varies in time, but we were able to track it thanks to this parameter. And we observed that, in fact, we satisfy the overall objective at the end. So even though the problem varies, so what we are aiming at even does not exist. There's no such a thing as a finite end that we should sample because it changes from time to time. Actually, we track it in real time. We learn it, right? And so the method still works. So thanks for the question. Yeah, we show that empirically. But it's cool because these problems are in practice do not have, of course, all these strong assumptions, but still the technique works.
Very good. Okay, well, I think we're just coming up to the hour, so we need to wrap up at this point. So it just remains for me to thank you again, Raphael, for a wonderful talk and a very interesting discussion there at the end. And thank you all for taking the time to attend today. And wish you all the best for the remainder of the day.
Thank you very much again. It was a pleasure. Thank you.
Thank you.
Thank you.
Okay, and I should also mention to thank Kate as well for all the arrangements and setting the seminar up. And hopefully you'll be able to join us for the remainders of the seminars that have been advertised. And I look forward to meeting you, Raphael, in a few weeks' time in person.
Yeah, excellent. Me too. Bye-bye, Sean. Bye-bye, everyone.
Bye, everybody.
Thanks very much.
Cheers.
Bye now.